Okay, so this is the Spring 2018 Midterm 2A Problem 3. So since it's given that it's an infinitely long, thin sheet of current, we can actually find the magnetic field of an infinite line to this problem, because essentially the sheet is made of infinite lines. So using Ampere's law, we're going to find the magnetic field of an infinite line. So we have an infinite line that's carrying current, and this is generating a magnetic field around the wire. Using our right hand rule, the thumb is a current, the fingers curving is the B field. The radius R, and we're going to find the B field of this infinite wire. So we're going to use Ampere's law. And Ampere's law is the integral B magnetic field on the loop, dl, which are the little segments that make up the loop, mu naught, which is the permeability constant, and I, which is the current in the wire. Since B is uniform and parallel to the loop, it becomes B times L, which is the circumference, the length, and mu naught I, so B, the circumference is 2 pi r, mu naught I. And so we get our magnetic field equal to mu naught I over 2 pi r. So now that we have calculated the magnetic field of an infinite line, we're going to apply this to our problem with the sheet. So I'm going to draw that out. We have our axis, and then we have the semicircle sheet. It has a radius r and theta. So if we choose a tiny element, we're going to call that di, and this di is just as this di will be generating a magnetic field around. So if di is coming out of the board, it's generating a magnetic field around the curving of the fingers. And this radius of this would also be the same as the one calculated for the infinite wire, because this tiny di is basically an infinite wire. So tangent to the circle is our dB vector, our magnetic field vector. And since it's a vector, it also have x and y components. Now the magnetic field actually only adds in one direction and cancels out in the other. So if we choose an element on the other side, it would also be generating a magnetic field, and the magnetic field will be tangent to the circle. So we're trying to find the magnetic field at the origin, so here it will be going in this direction. And since dB is a vector, it will have x and y components. So draw x and y components. And then what we realize is that our first tiny element and our second tiny element, dB, in the direction of y will cancel, and while the x components will add. We also defined our angle as theta from di to the origin, and the d and that line is a right angle with our dB vector. And since that's theta, the other angle has to be alpha, and our axes also make a 90-degree angle, and since that's alpha, the other angle has to be theta to make that 90 degrees. And so if that's theta, then we have opposite over hypotenuse, which is sine theta. And so for our dB in the x direction, we will be using dB times sine theta. Okay, so we're going to write out the magnetic field due to our tiny element dI. dB is equal to mu naught dI over 2 pi r our dI. So to find the current in our dI, we would just that would just be equal to the current over the length multiplied by the arc length of that tiny. So mu naught over 2 pi, change the R because it's capital R. We define it as capital R. And so our dI, our tiny element, will have a current, carries a current defined as the current over the arc, the current over the length, which is a semicircle, so it would just be pi r, and then multiplied by our our tiny element's arc length, which is r d theta. For tiny element dI. And it's r d theta because we're going to be integrating these tiny pieces to find the total magnetic field, which we will calculate next. And it would just be dB in the x direction. So So 1r cancels out on the top. So you get mu naught over 2 pi squared. 2 pi squared. So now we're going to calculate the magnetic field in the x direction. So taking our answer, we will now so we get dBx equals dB, what we calculated right before this, sine theta because we defined that angle as opposite over hypotenuse, so it's sine theta in the x direction. And then, so we're going to take our dB answer from the previous part, sine theta d theta. Now, integrating from 0 to pi sine theta d theta, that becomes negative cosine from pi to 0, which is 1 minus negative 1, which is equal to 2. And then our final answer comes out to be mu naught I over pi squared r in the x hat direction. So this is the total magnetic field generated, total magnetic field of the infinite sheet at the origin.